Alright everyone, we're going to get started. This week we have David Witmer talking about sum of squares for refuting CSPs.
Thanks a lot, Colin. So first of all, I have to tell you about refuting CSPs. So to do that, I want to talk about 3-sat. So what's the problem with 3-sat? So you have a bunch of clauses, each of which is an OR function on 3 variables. Maybe it looks like that. And of course, that has some associated satisfying set of assignments, anything but these. And maybe kind of combinatorially, it's just kind of this hyperedge with 3 variables. Then if you take a bunch of these things, that's pretty simple. You get a bunch of these things, you get 3-sat. And now you have a lot of these clauses that you want to satisfy. And now maybe combinatorially, things are a little more complicated. And dealing with this thing turns out to be NP hard. So this is, I mean, if you could understand all this, you'd solve P versus NP. So we can't do that. So maybe we'll study average case instead of worst case to get a better handle on, when you take a bunch of these things, does it become unsatisfiable? So random 3-sat's what we're talking about. So we have n variables, and we have 2 n literals, which is either the variable or its negation. And we have m constraints, each of which is this 3-variable OR function applied to 3 uniformly random literals. And maybe it looks something like this. All right, so what happens is you vary the number of constraints as a function of the number of variables. Well, this is a conjectured value here at which, for which on this side, an instance is satisfiable with high probability, and on this side it's unsatisfiable with high probability. And that's a conjecture, but there's a lot of numerical evidence supporting it. This is sort of what the world looks like. So here, the natural algorithmic task is to find the set. Yes?
What's the sense of high probability here?
What's
high probability?
That
like constant probability or like 1 - 1 over n?
Good.
1 - 1 over 1.
Yeah, let's go with that. I guess you can get pretty strong, if you're over here, probably something much stronger probability. Yeah, let's go with 1 last little bit. And that'll be what we'll use throughout. So here, the natural thing to do is to find a satisfying assignment. Over here is refutation, this problem I want to talk about, which is to find a proof of unsatisfiability. And we will be sticking over here for the rest of this talk. So what's a proof of unsatisfiability? Well, I guess it's some string and some verifier, some check that this proof is correct, and you should accept it if and only if your instance is actually unsatisfiable. So polytime refutation is to find a proof of unsatisfiability in polytime. You can also ask about non-deterministic refutation, which is showing that some poly-size proof of unsatisfiability exists, even if you can't actually find it efficiently. So what might a refutation look like? Well, here's one. If you somehow chose some instance and magically all 8 of these constraints appeared, you know it's unsatisfiable because you can't actually satisfy all of them. That's a pretty dumb example. So you need kind of a lot of constraints to find this thing at random. So can you refute with fewer constraints? So let's kind of talk about this task by, what's the kind of specification for the algorithm that we're looking for. So we want to take a random instance with n much bigger than n because we want it to be unsatisfiable. And we want to output either unsatisfiable or fail so that we output unsatisfiable with high probability. And if the instance is satisfiable, we output fail. We kind of throw up our hands and say we don't actually know. And that's fine to do that. So it's possible that there are instances that are unsatisfiable in which we output fail, but as long as that's small enough, we don't care. So this gets easier as m increases. That's what I was getting at earlier, and our goal is to refute with m as small as possible. So 3-sat people have thought about this kind of a lot. On the satisfiable side, you can kind of prove that it's satisfiable as long as you have fewer than 3.52 n constraints. recently there's been some work on algorithms that seem to work well in practice, all the way up to the conjecture threshold. On this side, we know that you can get polytime refutation as soon as you have like n to 1.5 constraints, and you can show there exists a small proof of unsatisfiability once you have n to 1.4 constraints. Here, who knows? It's still open to figure out what's going on there. All right. So, as I said, we're going to be talking about this side of the world. All right. So you can also ask about kind of stronger notions of refutation. So if you make opt be the max fraction of constraints that can be simultaneously satisfied, actually the world looks kind of like this, where you kind of cross the threshold, and all of a sudden, the maximum fraction of constraints you can satisfy kind of drops to about 7/8. And you can kind of 7/8 comes from the fact that if you choose a random string in like 0, 1 to 3, then it's going to satisfy OR with probability 7 or 8. Everything except 0, 0, 0. So this delta refutation is defined a proof that opt is at most 1 minus delta. And strong refutation is defined a proof that opt is at most a little over this expected value here. So you can kind of ask a similar question as before. Instead of saying that you want to output fail if everybody's satisfiable, you say, okay, output fail if 1 minus delta. If more than 1 minus delta fraction is satisfiable. And again, we can ask if we can delta refute within as small as possible. This makes sense so far? So then we can also consider refutation of other CSPs besides 3-sat. So instead of having an OR function, we can have some k-ary predicate P. We can again have m constraints, which is just P, each of which is P applied to k uniformly random literals. And we can kind of draw the same picture and ask for the same questions. This is what we're going to be talking about. So why is this problem worth thinking about? A lot of the applications come from the fact that refutation seems pretty hard, but somehow these random instances are kind of simple and easy to analyze and are nice to use in reductions. So there's been work in crypto and hardness approximation, proof complexity, learning theory that involve refutation. I'll talk about applications in crypto and learning theory briefly. So you can assume maybe that it's hard to refute a random instance of CSPP when m is like n to the c for some c that's of course bigger than 1. And what does that get you? Well, in crypto, it gets you evidence for the existence of a pseudo-random generator with pretty big stretch in NC0K. So that's constant parallel time. And a lot of people have kind of studied this setup. And learning theory gets you hardness of learning of concept classes that are somehow related to this predicate. And this is a line of work by Danielle et al. That's very nice. So motivated by these applications, our goal then is to prove refutation lower bounds for predicates other than sat, because that comes up in these applications. Superlinear number of constraints, because that also comes up in these applications. For example, in the PRG application, if you get more constraints, then you get higher stretch, and that's nice. And also for this kind of stronger delta refutation problem. So that's what we want to do. Now, what kind of algorithms are we going to prove lower bounds for? Well, that's SDP algorithms. So for now, let's think of an SDP as like this black box. You kind of solve some relaxation. You throw in some instance. You get out some number. And this is some estimate for the actual fraction of the actual kind of optimal fraction of satisfiable constraints. In fact, it's an upper bound. So here's an algorithm. You can solve the relaxation. You can say, my SDP think it's unsatisfiable. If so, I'll return unsatisfiable. Else, I'll return don't know. This gives you a proof because there's some SDP dual solution that will certify that this is that this is an upper bound on the actual opt. You can also do the same thing for delta refutation. So now, in particular, I want to talk about SOS refutation, which is a specific SDP-based refutation algorithm. So it's the sequence of increasingly tight SDP relaxations parameterized by something called a degree. The degree of D relaxation takes time n to the O of D to solve. The degree of intermediate relaxation actually integral. So all the feasible solutions are integral. And it captures many known refutation algorithms, also a lot of state-of-the-art approximation algorithms. And it also gets you kind of a lot of other nice results. For example, the unique games conjecture implies that SOS is actually optimal for worst-case approximation of CSP by work of Raghavendra. In addition, a lot of I guess the attraction of studying this has come from the fact that over the past few years, SOS has been shown to solve a lot of problems that were previously thought to be hard. So it's kind of taken a lot of hard examples we had for problems and shown that actually, in SOS you can actually solve these things. So it seems like a pretty powerful algorithm. And so we're going to try to prove low bounds for this. So that brings me to results. Any questions? All right. So to talk about my results, I need to talk about this notion of limited uniformity distributions. So you have some distribution D over 0, 1 of the K, which is inputs to some predicate. And we're going to say this thing is T-wise uniform if every set of T positions is the uniform distribution over 0, 1 of T. So here's an example. You have satisfying assignments for XOR, 3 XOR. And you can take them with each of these probabilities. And if you look at these two positions, 2 and 3, you see that this is indeed the uniform distribution over 0, 1, and 2. If you look at 1 and 3, you see the same thing. If you look at 1 and 3, you see the same thing. So this is 2-wise uniform. Of course, it's not 3-wise uniform because not all of the possible strings, 3-bit strings, are not represented here. All right. So we can also ask kind of how close you are to being T-wise uniform. And we're going to introduce this value here. So this delta P of T, it's something that depends on a predicate, and it's just the smallest distance you can find between a T-wise uniform distribution and a distribution supported on satisfying assignments to P. So this is how far your predicate is of supporting a T-wise uniform distribution. So here's an example. It's 1 and 3 set predicate. So you get 1 if you get exactly 1, 1, and you get 0 otherwise. And if you kind of sit down and think about it, you can see that this is a distance quarter away from supporting a 2-wise uniform distribution. And the closest thing there is this XOR distribution we saw on the last slide. And that's a quarter off because it puts a quarter of its mass on 1, 1, 1. And then you're 5/8 distance away from supporting a 3-wise uniform distribution, which is just the uniform distribution over 3-bit strings, which the expected value of the expected fraction of, what am I saying? The fraction of 3-bit strings to satisfy this is 3/8, so this is where the 5/8 come from. All right, does this make sense? Cool. All right, so what's been done in this area before? So we're going to, for convenience, let's write m is equal to delta, this constraint density, times n. And so Grigoriev and Chernobyk showed that if you make the degree n over delta to the 2 over k minus 2, you can't refute random instances. There's some value you can, up to this point, you can't refute instances of k sat and k XOR with high probability. So if you have, it's kind of a pain to read that, so you can just say, well, if you just want to make this degree constant so you get polytime refutation, you need m to be bigger than m to k over 2. And then in more recent work, Barak, Chen, and k-ary showed that if P supports a pairwise uniform distribution and the constraint density is constant and you remove a small number of constraints, then SOS can't refute. So this is removing a small number of constraints. So yeah, you pick a random instance and somehow you go and you can look around and find some constraints you can throw out, and then once you kind of throw out the small number of constraints, then you can show that SOS thinks it's satisfiable. And so we don't want to do that because we'd rather look at fully random instances. Okay, cool. So what's been done on the upper bound side? So Sarah, Ryan, and I showed that you can get polynomial time delta p t refutation when m is like much bigger than n to the t over 2, maybe by some polylog factor or something. Recently, Raghavendra Rao and Shram showed that you can kind of extend this out of the constant degree SOS regime to kind of super constant, and they get this very nice result here that generalizes this. So if we kind of stick with polytime, you get this picture here where you kind of become unsatisfiable here, and then you're kind of some distance away from, say, supporting pairwise uniform distribution. And you can kind of refute that much, and then you have how far away are you from supporting a three-wise uniform distribution? You can refute that much. It kind of keeps going like this in steps until you get to the actual kind of fraction of satisfying assignments, and then you kind of strongly refute there once you add in the k over 2. And so it's kind of a weird picture because there's these steps. You can ask, is this the best you can do? Turns out that it is. So what's our result? So let's say that P supports a t-wise uniform distribution over satisfying assignments. Then we show that this degree n over delta to the 2 over t minus 1 SOS algorithm can't refute a random instance of high probability. And so that means to refute polytime, SOS needs m to be kind of bigger than n to the t plus 1 over 2. And again, this is essentially tight by results in the last slide. And in addition, by work with Lee, Raghavendra, and Stoyer, this is kind of all you need to do to show that really any SDP needs this many constraints to refute polynomial time. And so any kind of algorithm in this kind of framework that I showed with that black box earlier, you kind of need this many constraints. All right. Also, you can talk about the stronger delta refutation problem. And so you take that same degree, SOS can't delta P of T refute plus some little of 1 with high probability. So it's kind of weird, all these parameters. So let's look at some pictures and examples and stuff like that. So back to 1 and 3 set. So we talked about this before, and so you can kind of plot what happens if you look at degree and number of constraints. So as number of constraints gets bigger, it gets easier. As degree gets bigger, you have a more powerful algorithm. So if you have few constraints, you kind of need high degree. If you have low degree, you kind of need more constraints, and you kind of have this nice trade-off. And so below this line, you can show kind of that your opt is at most 3/4, and kind of above this line, you can show it's at most 3/4. You can think about other predicates too, and somehow the picture kind of looks like this, where as you can kind of increase the degree to get stronger refutation, you can increase the number of constraints to get stronger refutation, you get some kind of trade-off that kind of goes in these steps. You can also look back at polytime refutation, and so we have this upper bound, and now we have kind of the matching lower bound, showing that pretty much up to this point, you can't do better. Are there any questions about the results before I move on? So for the rest of this talk, I'm going to talk a little bit about the SOS hierarchy to kind of give some more details about that. And then having done that, I'll give a very brief sketch of the proof. So what's up with all these hierarchies? So say you want to solve a CSP, and if you had something that would give you a distribution over satisfying assignments, that would do it for you. You would just pick your CSP, find some distribution over satisfying assignments, and just draw from it, and you'd be set. So you could kind of write this in this way. So you'd like to maximize the kind of expected fraction of satisfied constraints such that this mu is just a distribution over all assignments. If you do that, you can solve the CSP, you'd be very happy. Of course, this is NP hard. So somehow we want to make this tractable. And so STP hierarchies relax this to find objects that are not distributions but are somehow distribution-like. So you can kind of write something similar down. You can try to maximize the fraction of satisfied constraints, but instead of requiring mu to be a distribution, it's going to be something, a pseudo distribution, kind of a fake distribution that kind of looks like a valid distribution when you look at it with simple enough functions. You can do this with polytime. In polytime, if you kind of choose the parameter, right? So this is the high level picture. So yeah, if you want to solve the CSP exactly, you kind of set this thing up. So what's a distribution? Satisfies some normalization constraint, satisfies some negativity. Now what does SOS do? SOS also has some kind of normalization condition, but then it has some relaxed non-negativity condition. So instead of saying that mu is actually non-negative, you say that mu looks non-negative to simple enough functions. And so now mu is not really a distribution anymore, so this is actually not really an expectation, it's something that we'll call pseudo expectation. So now I have to tell you kind of what simple enough means. So simple enough means that this pseudo expectation, if you take the pseudo expectation of a function that is a square of some polynomial of low enough degree, then it's not negative. So if you say, you know, if I give you this pseudo expectation, you say, you know, I want to see if it's actually, you know, if this is actually a real thing. You might say, okay, well, I'll see if it behaves right on squares, which should be positive. And so, you know, you kind of throw all these squares of polynomials at it, and if you say, huh, I looked up the degree r and can't break it, then, you know, this is what you're looking for. Does this definition make sense? All right. So yeah, we're going to call this thing an R round SOS pseudo distribution. And as I said before, this will actually solve your CSP when r equals n, in particular because it's going to be a real distribution in that case. This is you can solve this thing with an STP of size n to the O of r. So what's our goal? It's to construct a pseudo distribution such that normalization holds, this relaxed non-negativity thing holds, and we satisfy all constraints. We're going to ignore the whole delta refutation business here and just focus on showing lower bounds for just the basic refutation problem. So what's been done on this in the past? Previous work, Ryan and I showed that you can get a pseudo distribution thing that satisfies weaker.
So what is hierarchical about that? Where are you going to get to that?
This becomes a stronger and stronger condition as this value r increases.
Okay.
So that's the degree. I don't know why I switched r from r to d, but yeah, the degree is what makes it hierarchy. So as you increase the degree, you're asking for non-negativity of like more and more and more of these functions, and
okay, and then caps that at n.
Yeah.
So if you're trying to use this to refute, you want to show that like for any pseudo distribution, the fraction is less than the expected.
No, I want to show there exists a single.
Oh, but you're going to show there exists.
It's a lower bound.
Yeah, so you're proving the lower bound. That's what I'm getting at. So yeah, this is for like the lower bound. So you want to show there will be some bad pseudo distribution which trick like SOS and they're thinking and satisfiable. Okay.
Exactly. Yes. So what do we know from previous work? Well, you can find something that is almost there, except it has a kind of a different condition here. So this is a weaker condition where you say, well, our pseudo expectation is not negative for positive functions f that depend on most r variables. And you can show that this is weaker than the previous condition. So we know we can do this. So that's kind of a starting point. And in fact, we'll kind of use the same solution and show that it actually satisfies the stronger condition on the previous slide. All right. So now that's SOS. So now let's move on to a sketch of the proof. To do that, I'm going to kind of split that into two parts. I'm going to talk about how to define the pseudo expectation, the pseudo distribution, and I'm going to sketch a proof showing that this relaxed positivity condition is satisfied. Is everything clear up to this point? Any questions? All right. So before I jump into the pseudo expectation, I'm going to kind of jump to the punchline, which is that all this works because random instances have high expansion. So we're going to think about an instance as this factor graph form where you have some variables. It's a bipartite graph where you have variables on one side, constraints on the other. They're connected if the constraint contains the variable. Here's an example. And if you take a random instance, you get a random factor graph, and this thing is going to have high expansion. So particular, what that means is that every small enough set of constraints kind of has a lot of variables. So you don't have, some, set of variables that has like tons and tons of constraints all in the same variables. It's like really dense like that, like packed in like that, because that wouldn't really happen at random. Instead, kind of, every small enough set of constraints kind of spread out over an appropriately sized set of variables, as you'd expect at random. That's high expansion. That's really what makes this work and kind of all previous lower bound work go. All right, so on to the pseudo expectation. So I'm going to define a planted distribution on assignments of small sets of variables first, and kind of use that to define the pseudo expectation. So here's again this factor graph, and we're actually going to assume now that the uniform distribution over satisfying assignments to our predicate is Ty is uniform. Because this works for, like I said, the result. If P supports some Ty uniform distribution, that's fine. But just to kind of simplify notation, we'll just assume the uniform distribution works. So let's define this A to S to be the uniform distribution over satisfying assignments to constraints covered by S. So S is some set of variables. So here's an S, and S covers what constraints? S covers this constraint here, and this constraint here. Oh, sorry, I switched to plus. This is XOR plus or minus 1. I did that accidentally. Sorry about that. So these are just XOR constraints, and the variables now plus or minus 1. So this is an example here. And so yeah, here are two constraints that are covered by the set of 4 variables S. And so then A to S becomes this thing here. Take each of these to probably 1/8. So this will satisfy both those constraints. And so what we really want to do is define our pseudo expectation to be, some monomial XS to be just the expectation over kind of its corresponding planted local distribution like this. And that's a nice thing to do because then you'll satisfy all the constraints by construction. So unfortunately, it's not quite going to work out. It violates kind of this thing called local consistency. So it turns out, and it kind of makes sense this would be the case. You'd really like it to be the case that if you take your monomial and you take the expected value over this planted distribution, it seems like it should kind of be the same as if you took the expectation over kind of a larger, planted distribution on a larger set. And you need that for example, Shirley-Adams, and this is how kind of probability distribution should behave, that you should be able to kind of marginalize over them, and so this is how things should work. But as far as we've gone, we haven't achieved that yet. So here's an example of a little factor graph that breaks this. So here are two constraints, XOR again, plus or minus 1. And so you can look at the expectations for these planted distributions of x1 times x4. And if you just look over this planted distribution for x1, x4, then you see that no constraints are covered. You can choose things uniformly at random, and you get expectations 0, so plus or minus 1. If, however, you look at the whole set of 4 variables, and you look at that planted distribution, you see that the expected value of x1 times x4 is -1, because to satisfy both of these constraints, that means that x1 times x4 equals -1. So this does not satisfy this consistency condition. All right, so what do we need to do? We need to be a little bit smarter about how we define this pseudo expectation in terms of these plane distributions. So we need to kind of figure out, maybe we can kind of grow our set a little bit such that we've kind of captured all the variables and all the constraints that kind of affect us. So the closure, it's a small subgraph of our factor graph that's really needed to determine the planning distribution on S. It's kind of intuition. So to do that, I have to kind of give a preliminary definition of this S-closed subgraph. So an S-closed subgraph is one in which every constraint vertex has degree at least t. recall that we're assuming that the uniform distribution on satisfying assignments is Ty is uniform. And every variable vertex with degree 1 is contained in S. So S is a set of variables. This is here because of Ty's uniformity. So if you had a constraint vertex that had degree less than T, it wouldn't really affect you because this distribution we're drawing from is Ty's uniform. So once you look at like fewer than T things, it's just going to be the uniform distribution. It's not going to. It doesn't really affect what you're trying to do. And over here, if you had a variable vertex that was not an S with degree 1, you could just kind of marginalize this out and it wouldn't affect what's going on with S. So this definition is really just keeping everything that matters when defining these distributions. So here's an example of 1-4 closed subset. So if you take everything, it's 1-4 closed. Because these guys have degree 1, and these guys have degree at least 3. Oh, T equals 2. Sorry, we have degree at least 2. So if we kind of taken this larger set on the previous slide, maybe we would have been okay. So motivated kind of by all these things, we're going to define this closure of S to be the union of all small S closed subgraphs. So I'm not going to say what small means, but it's just some parameter.
So when you say constraint vertex, do you mean so S is a subset of like the left partition?
Yes.
So it's the constraint vertices are the ones that are covered by, that are like, for which all of its neighbors are in S?
This is a subgraph of the factor graph. So it actually has both.
Oh, that's right. Oh, I see.
Yeah.
Oh, sorry, constraint vertex. Oh, I see.
Yeah.
Yeah.
So these are, this is kind of all variables and constraints that kind of affect what the distribution on S should be. So now we'll make our definition. So the pseudo expectation of this monomial is just the expectation over its kind of this planar distribution. But now you're looking at this whole, instead of looking at S, you look at kind of this larger closure of S. So closure of S, it's easy to see this actually just contains S. So that's the pseudo expectation we're going to look at. And this is one that's kind of cropped up in, this is slightly different, but it's, similar things have kind of cropped up in all the previous ones in this problem. All right, so that's what I'm going to say about this definition. Are there any questions on that before I move on?
So I assume, because the motivation for the superset, like if you take the superset, but you end up with the same pseudo expectation, that's no
yes, yeah. So now you get this kind of low consistency conditional.
Okay.
Exactly. Yes, thank you. Because you've kind of, everything that could possibly kind of cause a problem is now taken care of.
I feel like I'm just quibbling about rotation now, but just to make sure I understand. So like, when you say eta subclosure S, closure of S is a graph, right? A subgraph, or is that a, am I confused on that? Because it's like a union of subgraphs. So like
yeah, sorry. I was trying to make things simpler, but I made things kind of more complicated. Yeah, so given a subgraph. So it would just be like all the left vertices. And all the corresponding variables, yeah.
Okay, cool.
This is kind of the natural plane distribution on kind of everything that really affects you. That's the intuition for what's going on. All right. So how do we prove that this positivity condition holds? So first of all, an observation from Barak and k-ary from their lower bound is that if you prove positivity for some orthogonal basis, that's enough. So let these FIs be a basis for the space of degree D polynomials such that it's orthogonal under this pseudo expectation operator, and positivity holds for the basis elements. If you get this, you're set. You get this positivity condition holds for everybody, because if you write your polynomial in this basis, then you can see that the value is not negative. So the orthogonality kills off all the cross terms, and you're left with just these terms, and you're done. So we would really like to find such a basis. So how can we find an orthogonal basis? Well, if you remember from linear algebra, you can just run the Gramschmidt process. So maybe we should start with this kind of monomial basis, which is just kind of all the monomials. And we should try to do this. So here's what you start with, and you kind of subtract off the component of x1 in the direction of the previous guy, and you kind of continue in this manner. And orthogonality will hold by construction. So that's kind of nice. So then you just need to show that this positivity thing holds. So I want to show this. So for every basis element, that the pseudo expectation of that guy squared is at most 0, or at least 0. Sorry. Like I was saying before, we sort of already know a little bit because we have this. We know this kind of relaxed Rayleigh-Adams condition holds for our solution already. So we have this lower bound from before, and so that means that it suffices to show that the support of our basis functions is small. So recall that kind of relaxed non-negativity condition was that if the support is small enough, then you get non-negativity. And so if you show that the support of this guy is small enough, then you get non-negativity and you get what you want. So this is what we're going to be trying to do. All right, so let's see what happens when you run Gramschmidt. So here's a instance or a sub-instance or something, some group of constraints and variables. And what these constraints on these variables, what they do is they fix x1 to 1. So you can see that if you kind of multiply all these together, that everything kind of cancels out except for x1. So this kind of forces the pseudo expectation of x1 to be 1. Now you can say, okay, what if I have an instance with 2 of these guys? Now I've kind of have something similar, and I kind of force this variable z1 to be -1. And so now, of course, these things they're completely independent. And so the pseudo expectation of x1 times z1 is now -1. So they're not orthogonal. So how does Gramschmidt take care of this? So you can even do more. You can say, okay, I have a bunch of these blocks that set a bunch of different variables, and now I have that every single pair of these xij guys is kind of not has inner product 1. So yeah, how do I get orthogonality here? So I run Gramschmidt. So I orthogonalize against the degree 0 monomial, which is 1. I get this guy, and then I can go back and I can say, okay, now do I have orthogonality? And so I write this all out, and it turns out that I do. This is what Gramschmidt's doing in this very simple case. Maybe you could hope that maybe you just need to do a little bit of orthogonalization. You're very happy here because there's the only variable occurring in this thing is still xi, so that's fine. You can say, okay, maybe I can just deal with degree 0 and call it a day, but it's not quite true. You can look at this example, which is a star. So you have one variable x0 that occurs in a bunch of different constraints. And each of those constraints has another 2 variables. And so what happens here, so try orthogonalizing against the degree 0 monomials. You get, these can be your basis functions. You look at their dot product, and you see that you get 1. So that's not orthogonal. So now, of course, what you should do if you're running Gramschmidt is to orthogonalize against degree 1 monomials. So if you do that, you get this guy. And now, things work. You get 0. You can kind of keep doing this. Now to kind of show the intuition that we're going to need, I'm going to do a slightly different kind of proof of this simple calculation. So again, you want to kind of go and try to see what this dot product is. And you can write this expectation as the expectation over this conditional expectation with this x0 here. But now, of course, x0 is, given a fixed, value for x0, these constraints involved, in yi, you're talking about, this constraint involving, kind of xi, zi. And once I've kind of fixed x0, these things are now independent. So I can write it like this. Now I can write this conditional expectation out, and it's something like this, where this is an indicator function that xi is equal to b. But this is now degree 1 term. because it's just depends on one variable. And so, and I've already told you that I've orthogonalized against degree 1 monomials. So this is something that I've orthogonalized against degree 1 monomials times degree 1 monomial, so it has, you get 0. So these guys are 0, and this whole thing is 0. This is another way of seeing that Gramschmidt's kind of doing what you want it to do. And this is really what gives us the intuition behind our proof. This involves the notion of witness sets. So we're going to say that vertex sets S and T are C separable if removing a set of at most C vertices disconnects them. So here's the idea, motivated by the last slide. If S and T, if you kind of separate them by ripping out 3 vertices, then if you run Gramschmidt up to degree C, then you get functions, the corresponding Gramschmidt functions for those monomials are going to be orthogonal. And so here you kind of ran Gramschmidt up to degree 1, and now because they were one connected, like things were orthogonal and you were really happy. So maybe that kind of holds more generally. That's the hope. And so you kind of flip that around and you can say, okay, well say we run Gramschmidt up to degree C and say that we get that the basis functions we get are not orthogonal, then that must mean that these sets are not actually C separable. So intuitively what that means is that there should be some kind of dense set containing S and C. They're like really well connected. There's kind of all these different paths between them. There's all these things. So there's kind of if you kind of just squint at it, I'm not going to actually give any kind of formal details here, but if you kind of squint at it, that means that you kind of have some smaller set of variables. There's a bunch of different constraints connecting them. That's bad for expansion. So this is like a kind of a set with poor expansion that kind of certifies that this is not equal to 0. And so this set sort of witnesses the correlation between YS and YT, and furthermore is doesn't have very good expansion. And so recall that we said that random instances have high expansion. And so this is what we're going to use to show that this can't happen too much. Does that make sense? Any questions about kind of the high-level idea there? Yes.
Sorry, why does high expansion mean that things aren't C separable?
I didn't really say that formally. So I mean, you can imagine that if you have like 2 sets of variables and like a lot of different paths between them, then somehow that means that you kind of have a lot of different kind of paths, a lot of constraints kind of involved in connecting them on maybe not too big set of variables. And this is something that is not good for expansion because you have kind of some set, and there's a lot of different constraints that are kind of in that set, not going outward. Yeah, and this is not quite how it goes. I'm just kind of giving intuition because the actual proof is sort of a technical thing. It's not very helpful for seeing this. All right, so.
This is where you use randomness of the instance, so you cannot have such correlation.
Expansion is all you need. So.
No, but I mean, in this thing, when you finish this argument, you would say this is not possible because the instance is random or something? What's the...
Yeah, so, well, I haven't quite laid it all out yet, but what's going to happen is you're going to say, okay, well, if you do Gramschmidt, you come up with some basis function that when you're doing Gramschmidt, you're kind of dot product, you're taking the dot product with a lot of different guys all along the way. And so say a lot of those come up non-zero. Then that means that you have all these kind of sets that have these sets that kind of certify their correlation. And so you kind of end up with a big set that has a big set that what am I saying? It violates expansion. It ends up violating expansion. Yeah. Does that make sense? I mean, I'm not actually saying anything. Yeah.
So are you saying that like your argument works? Like I don't need to assume that my instance is random. I just need to assume that it has high expansion. Then I'm good. It's just so
pretty much.
Okay.
And that's not just our work. That's how all other lower bounds for this go. All right. So I'm going to give a really handy.
But is this somehow related to something like width in this?
I mean, the reason why the width stuff goes is because of expansion. So, in some ways, but is it directly related? I mean,
no, because width is another like thing which is implied by expansion, but is sort of more intrinsic to
I guess like
CSPs.
what's width here? Because I mean,
Yeah,
I feel like you kind of need to do resolution. It's really not clear what resolution is. So we were actually talking about this a good amount. Is there some notion of resolution that'll work for arbitrary predicates, and we didn't. We kind of got stuck on that. And so yeah, this proof is not. I mean, as far as I think about it, is not really too closely related to Schoenbeck's. All right. So when you're doing Gramschmidt, you kind of fix some order on your sets because your monomials each correspond to some set, and you do this in such a way that it respects the kind of sizes of these sets. And for notation, I'll make PR of S be the predecessor of S in this order. And so we can do kind of this modified Gramschmidt thing, which kind of breaks up Gramschmidt into different stages. And so if you're trying to figure out the Gramschmidt guy corresponding to monomial XS, you kind of start by orthogonalizing against just 1. And then from there, you kind of take what you've done so far and orthogonalize against the next guy. You kind of iteratively do that. And then in the end, you kind of have orthogonalized against everyone you've already looked at, and that's what you end up with as your the function. This is just kind of rewriting out what Gramschmidt looks like. Okay, so if YS has large support, then kind of along the way when you're doing this process, you run into a lot of these sets for which the corresponding guys have some correlation. So their dot product is just not 0. And intuitively, at least, there should be kind of these witness sets that kind of certify that have poor expansion. And so you kind of take all these, there's a bunch of this happens a lot. You kind of, somehow take the union of all these, and you get this set that kind of breaks expansion. And that's how you show that you can't have large support. So I drew a picture that's probably not very helpful. So you're doing Gramschmidt, and you say, aha, I did Gramschmidt, I did a step, and it turns out there's this guy T1 who kind of has some correlation with this Y has 0, and so I have to kind of account for that. So I have I can find some kind of set witnessing that contains S in case the support of Y sub T1, and it has the property that support of this whole guy is contained in that, and expansion is not so hot. Okay, so then I do it again, and now I kind of look at the next guy T2. Same thing happens. Now I can kind of grow that a little bit in such a way that now the whole support of this guy is contained in that. I still have kind of this kind of poorly expanding set, and I kind of keep going like that. And in the end, I can kind of do this in such a way that I get a kind of a set that has kind of bad expansion and contains the whole support. And so if the support were large, then this would break expansion. That's kind of how it goes. I'm not going to really give any more details than that. Are there any questions? That's kind of all I have to say. So this is what we showed. There's some kind of lower bound of the degree that SOS needs, and in particular, if you want to do polynomial time refutation, you need this. And that's it. Thank you very much.
So because all you need is expansion to prove lower bounds of this sort, is there in this part of theory, is there a sense of CSPs that have high expansion that aren't just random CSPs that people talk about?
Like kind of natural examples that aren't random?
Yeah.
I don't know anything off the top of my head. I haven't thought too much about that. A question that comes up kind of related to what you're saying, though, is, because of all our lower bounds deal with expansion, you can ask, does expansion mean it's actually hard? So you can say, is there some distribution on highly expanding instances that actually you can refute? And that's, I don't know of anything that is like that, and that would be a really interesting question.
So for this delta refutation, you will change this eta s to be all assignments which 1 minus delta satisfy s or something?
So you construct the plane distribution, you do it kind of based on distributions for each constraint. And you kind of say, okay, I look at this set of vertices, and I look at kind of the distribution over kind of satisfy all the constraints. And so instead what you do is you kind of switch out that uniform distribution for whatever your T-wise uniform distribution is that's delta far from satisfying, and you just throw that in there instead. And so what it looks like is you, for every constraint that's covered by your set of variables, you draw from its corresponding distribution, and you condition on everything being consistent on the variables that are contained in multiple constraints. It's the same that thing that comes up in the Benabas et al. Trial item stuff. It's all the same distribution. And so there they just say that you consider, say, pairwise uniform distribution support on satisfying assignments, but you can just switch that out for, in our case anyway, for a pairwise uniform distribution that's only right one last delta fraction of the time. Yes.
So when you're counting the number of constraints, is each constraint defined? Is each constraint like by definition a three-way or a variable, or can it be more general? Like what counts as a single constraint when you're measuring like how many constraints you're going to have?
Yeah. So the model we're looking at is. Well, I guess you're talking about more what is the problem. And so, yeah, each constraint is, some predicate. In this case, anyway, it's going to be some function, a predicate. It's a function that takes k bits to 1 bit. And you're going to, so each constraint is this guy applied to some k variables, or their negations. And so you're going to ask that evaluates to 1. And so that's one constraint. You kind of have a big list of those. So then
for every problem instance, you essentially have m predicates, each m potentially up to k-ary predicates, and that's how you define. So like a k is 3, this would be like 3 set, for example.
Yeah. So it depends. So there's other. So the way we're looking at it, we're only looking at one predicate. Yeah, for a given instance, but you can say that you can consider CSPs that have multiple allowed predicates. That's something that people do sometimes. If you're talking about 3-ary predicates, yeah, there's sat, there's 3 XOR, there's this satisfying exactly 1, satisfying there's a lot of different things that you can look at.
So then, see, I guess the question I'm asking is that so any 3-set problem you can look at it too is like so you can look at a 3-set problem as a collection of like 3 boards, or you can look at that thing as one big predicate that happens to include all the things. Are you looking at them in both ways? And
no.
How do I count the n? I guess is what the big question is.
No, so we're looking at 3 sets. So a predicate is a specific form. Literal 1 or literal 2 or literal 3 equals 1. That's what we're looking at. So if you're talking about kind of sat generally, yeah, you have something in, say CNF form, you could have, multiple, different arities, for the clauses, who knows. But no, we're not doing that. Everything has the same arity. Yeah, it's much simpler than that.